been requested to make this video, so thank you, Joe, for requesting this video. I definitely got this one wrong the first time. I had an idea what to do, but didn't work out. I'll probably point out where I slipped up when I tried to answer this question. So, as usual, read the question 5 to 100 times. And these are the details, the relevant details, well, some of them to begin with. We're given two random variables. They actually tell me what to call them, so x and y. And it's pretty clear, I think, sort of the setup, what the question is at least, that's important. X is the number of rolls needed to obtain a 5. Okay, we have fair dice, so obviously 6 sides. And y is the number of rolls needed to obtain a 6. You should definitely, right off the bat, you should be familiar enough to realize what type of random variables these are. They're both geometric random variables where we're starting at 1, right? This is the number of trials before the first success. For the random variable x, a success is getting a 5, and for random variable y, a success is obtaining a 6. So they're both identically distributed, and we're after a conditional expectation. We want the expected value of x given that y is 2. In other words, we want the expected number of rolls to obtain a 5 given that our first 6 was at 2, was the second roll, right? Because y is the number of rolls to obtain a 6. So what you should be thinking here is, I'll just sort of help you intuitively. This is my first roll, not a 6. This is the second roll, is a 6. Then, I don't know. I don't know what happens after that, right? Dot, 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 dot. But this one's definitely not a 6. And this is where you can make, this is probably, for me personally, this is where I messed it up. Because we're going to have to compute a probability here, and it definitely hinges on the fact that this is not a 6. So, what's going to be my setup? My setup here, to answer this question, I'm going to basically use a mixture, as I've done before in previous videos, but it's not your sort of conventional type of mixture. Let me show you what I mean. This is what we're looking for. So this is what we have. The expected value of x given y equals 2. I'm going to write down what the mixture should be, and then we'll think about why it makes sense. Okay? So, if you recall, if you're going to set up a mixture expectation problem, you need to make sure that you're involving an event and the complement of that event. Let me show you what I mean. So, this is equal to the expected value of x given x is, now what can x be? Remember, when you think about this, you say, when can the first 5 appear? Well, the first 5 can either appear when the rolls are less than 2. Okay, if the rolls are less than 2, that means x equals 1. X equals 1. Times the probability x is 1. Or, okay, if the number of rolls needed to obtain a 5 is not 1, what is it otherwise, given that y is 2? Well, it's either the first roll or it's the third roll or greater. It's not the second roll because the second roll is a 6. So, or, in other words, plus the expected value of x given x is at least 3 times the probability that x is at least 3. So this is what we need to compute on the right-hand side, and even if you got this far, which honestly it's been a while since I did this problem, but I think I got this far. As I mentioned before, I did get this problem wrong, but I think I had this. I did have this, but I messed this up after this actually. So what can we say now? What can we say now? Just think about this quantity for a second. You want to just think about sort of logically, what does this mean? I'm saying, what's the expected number of rolls to obtain a 5, given that the first roll is a 5? Well, 1, right? I mean, think about that for a second. Obviously, I mean, we're saying that we rolled a 5 on the first roll. So the expected number of rolls is 1. Okay? What's the probability that x is 1? Now this is where you have to think about this. Think about this little example I just sort of gave you. What's the probability x is 1? It's not 1/6. Why is it not 1/6? The probability the number of rolls needed to obtain a 5 is not 1/6. Why? Because it's not a 6. Okay, let me repeat that. If I want to compute the probability that the number of rolls needed to obtain a 5, okay, is equal to 1, we know it's not a 6 because the very first 6 appeared on the second roll. So this one, how many choices are for the first then? Given that the second is the first 6, there's only 5 choices. So this is 1/5, and this is where I screwed up. This is 1/5. Pretty tricky if you ask me. I'd say that's difficult, just my opinion. All right, let's move on. How about this? What is the expected number of rolls given? Second number of rolls to obtain the first 5, okay? Given that the number of rolls exceeds basically 2, greater than or equal to 3, right? This is where you actually, and I could write some things down, but if you just think about this intuitively again, remember that this is a geometric distribution. Geometric distribution is memoryless. Okay, what that means is that in terms of expectation, we're going to compute the expected value as you always do. Remember, the expected value of geometric is 1/p. Okay, so just imagine we're only concerned for this portion right here. Here's the first roll. Here's the second roll. Here's the third roll. We want to know the expected value past this. We want to know the expected value of x past the third roll or greater. All we need to do is say, look, these 2 rolls happened, okay, and they were not a 5. So we're talking about 5, right? These 2 rolls happened, they were not 5s. So what's the expected value past this? Remember, the geometric distribution is memoryless. So this expectation over here is exactly the same as it would be previously. So it's just 1/p. So the first 2 rolls, we just let them happen. Okay, so this is the first 2 rolls. So we need to add those. So number of rolls, we had 2 plus 1/p. 1/p is the expected value of x. Because we're given that it's greater than or equal to 3, and x has the memoryless property. Okay, so let me just leave that for now. Times the probability x is greater than or equal to 3. This is another place to get hung up on. This is another place to mess up. Given this question, we know that the second roll is a 6. Okay? Therefore, in terms of the number of rolls we need to obtain a 5, it's either 1 or greater than or equal to 3. So in the context of this question, these are complements of each other. These are complementary probabilities, and they need to be that way in terms of the formula to work, but they also need to be that way in terms of the context of the question. So if the probability x is greater than or equal to 3 is the complement of x being 1, and the probability of x being 1 is a fifth, well, I need to take 1 minus a fifth. That's 4/5. So this is 4/5. We're pretty much there. So this is equal to 1/5 plus, what is 1/p? Remember, p is the probability of success regarding the random variable x. All right, well, the probability of success there is 1/6. I mean, what's the probability you obtain a 5? Okay, well, 6 choices, 1/6. So this is 2 plus 1/6. So this is, this is equal to 2 plus, p is 1/6, 1/1/6. Maybe I'll just write it. 1/1/6 times 4/5. Okay, hopefully that makes sense. I mean, this is just the expected value of a geometric random variable. So this is equal to 1/5 plus, this is 8, right? 1/1/6 is 6 plus 2 is 8 times 4/5. Do whatever you do. I mean, just use a calculator if you want, or add these, multiply, add the fractions. This gives you 32 plus 1, so 33/5, which is 6.6. And you're done. if you eventually get the program Adapt, because they do mix in SOA questions into that program, I think they rate this at like a level 7 or something. My opinion, much harder than a 7. Just my opinion. Difficult question. Thank you, Joe, for requesting it. Comment below if you have questions or just comments. Thank you.